Hi, my name is Prakash Gupta, and this is my physics lab report for Lab 2. So let's get started with an introduction. This lab had the goals of describing a motion of an object traveling in two directions according to projectile motion, with an added challenge of looking at how drag may affect this motion. For instructions, we were to take a video of a projectile doing such, and then analyze that video with Tracker to get real-world data. Then we were to develop two computational models using GlowScript, one with projectile motion and one compensating for air resistance. The principles in play here are Newton's laws, kinematics, and air resistance. And our results showed that the simulations only mostly resembled our real situation, implying there were some discrepancies due to um, false initial conditions or false assumptions. Let's jump into experimental design, where we see that to obtain our video, we manufactured the required motion by tossing a whiteboard eraser at an angle in front of the wall and a meter stick, and we recorded this using a phone. Our system here is the eraser, and our surroundings were the room and the earth. We also used a scale to measure that mass. Um, Based on Newton's laws and on the kinematic conditions, ignoring air resistance, an object thrown would act as a projectile and move according to the equations. And these conditions are satisfied in this situation as no other forces than gravity, which is constant, act on the eraser once it's been thrown. Let's take a look at that video. As you can see, we threw the eraser and it moved. So our next step was to create some simulations. And from the video, we gather a lot of information about initial conditions, and we can use that to build our kinematic model. Um, and once we have that, we can use Newton's laws and the velocity and position update equations shown below, to build our predictive model. We start by defining initial conditions, starting at the origin with an initial velocity as given. And we know that our projectile motion has constant velocity in the x direction, and that our launch angle was measured at 75 degrees. We also know that F net for the kinematic model is just gravity in the negative y direction, but for our drag model, we also have drag in the direction of velocity, as given by this equation below. Finally, we print that data out after we loop and update so that we can use that for data collection and graphing. Let's look at that code, which will show the same things that we just discussed, defining FNet, using our position and velocity update equations, increasing our time, and making our plots. We also have our vector arrows. And then for data analysis, to analyze that video, we uploaded it to Tracker as mentioned, and we exported our data from computational models and reconciled that into a combined Excel graph, compare how these results fit each other. But first, let's look at results from the kinematic situation, where we can see what we expect for parabolic trajectories and linear velocities um, and position versus times for the x direction. We also can see from the drag that we don't have linear velocities and that our would-be parabolic trajectory is slightly skewed. So let's look at the overall results here. And we can see that our gravity simulation was too high, but had a similar final endpoint, whereas our drag simulation did lower it slightly, lower our peak, but cut it off too soon. And that implies, we can see from this that there are some significant discrepancies between our data and our simulations. And let's talk about why. So some sources for that error could account from issues with our tracker output. It could also revolve around aberrations from the non-uniform shape of the eraser and the fact that it turns in midair, as we saw in the video, and the angle may have been slightly or maybe moderately different from our measured angle, and that would impact our simulated initial velocities. It might also be the case that our drag was having a greater impact in one direction than the other as a result of that angle. Let's talk about some what-if questions. So if we threw the object straight up with the same initial speed, we can talk about the time it would take using the time equation, which is 2v0 y over g. And we can see that if we throw straight up, all of our velocity will be in the positive y direction. So this value would be greater, and thus the time would take longer. And regarding terminal velocity, from our graphs, we didn't see any leveling. So our velocity was from our drag velocities, there was no leveling, so we didn't find a terminal velocity. And if we wanted to, in that case, we would need to drop it and have them fall for a longer period of time so that we can actually ensure that we achieve enough deceleration to reach terminal velocity. Thank you.